All right, you guys did a nice job last week with the central angle theorem and the inscribed angle theorem. We're going to bring those back really quick to review and then start a new one called a circumscribed angle theorem. So our central angle theorem came when we had a central angle made up of two radii, made of two radius. And the central angle theorem told us that whatever our central angle was, the corresponding arc, so the one that went from the same endpoint to endpoint, was exactly the same. So central angle equaled the corresponding arc. Then we talked about our inscribed angle theorem, and the inscribed angle is made of two chords. And those chords were something that went from one point on the edge of the circle to the other point on the edge of a circle. So something like that and something like that. So 1 point on the edge, 1 point on the edge. And our inscribed angle was always along the edge of a circle. And our inscribed angle theorem told us that our angle was equal to half the arc. And our arc is the same as double the angle. So if this was 30 degrees, our corresponding arc would be double that. So that would be 60. Or if this was 100 degrees, our angle would be half of the arc. So that would be 50 degrees, something like that. So just remember, the angle is smaller than its corresponding arc. That's what we should have learned last week. Then this week, we are talking about the circumscribed angle theorem. Now, you might have heard this circum word before, like circumnavigate. Ferdinand Magellan circumnavigated the world. He sailed all around the outside of the earth. Circumscribed just means outside of a circle. So if we have a circumscribed angle, that's this angle out here. It's made up of this piece right here and this piece right here. These are what are called tangents. And this is tangent. And what is a tangent? Great question. So I should write here. Made of two tangent lines. So a tangent line is a line that's on the outside of the circle, and it intersects with the circle exactly one time. And it's perpendicular. So both of these are perpendicular to a radius. So we have two tangent lines. They make up this angle out here, and this angle, what our circumscribed angle theorem is that the angle, the circumscribed angle is supplementary to the opposite central angle. Now, this word supplementary, hopefully you remember, it means it adds to 180 degrees. So this angle out here, our circumscribed angle, and this central angle that's across from it, these two angles, when you add them together, they equal 180 degrees. And today we are going to talk about why. So before we really get into how this theorem works, we're going to talk about why it works. So if we look, the circumscribed angle theorem, it's a circumscribed angles are supplementary to the central angle. Okay, so let's talk about why this works now. So if we look here, we were talking about how this is a radius and this is a radius. And what we know about radiuses, radii, I'm not really sure what the plural is. Let's say radii. The radii is the distance from the center of the circle to the edge of the circle. It's going to be the same no matter where you put your radius. So if I put another one over here, it's going to be the same distance as both of these radii that we've already drawn. But since a radii is the same, we can say this is congruent to this, meaning this radius is the same distance as this radius. Then we put on two tangent lines. So these are the lines out here. They intersect with our circle exactly one time. So these points right here, despite my not perfect drawings, the idea is that they intersect one time. These are our tangent and tangent. Now, this tangent is perpendicular to here and perpendicular to here. So a tangent meets exactly one spot, and that point is, it's called a point of tangency, which you don't need to remember. But this point of tangency is perpendicular to the radius that would intersect right at that exact same point. Same thing here. Now, here's what I want you guys to look at. And this is the whole reason that all of this works and why this theorem works. If I wanted to write a proof, I could. I'm not going to for this video. But we have a central angle here. We have a circumscribed angle here that we're looking for. And we know that these two are perpendicular angles. If we look at this shape right here, hopefully you remember back in chapter, I want to say it was chapter 10, we talked about area and we talked about different quadrilaterals. Quadrilaterals meaning four-sided figures. We have a four-sided figure right here. And we know that two of these sides are congruent, and we know we have one set of opposite angles that are congruent. So if you remember back, whenever you have a four-sided figure with one set of opposite congruent angles, we had a set of adjacent congruent sides. That means this is a kite. And if this is a kite, that means these guys, these two tangent lines, also have to be congruent. And that means, since we have a kite, it's a quadrilateral. All quadrilaterals, the interior angle sum is 360 degrees always. We could go into that n minus 2 times 180, talk about how there's four sides. So 4 minus 2 times 180, that equals that 360 degrees. So because of the interior angle sum, we know that 1, 2, 3, 4 angles all have to add up to 360 degrees. Since this is 90 degrees, and this is 90 degrees because we said they're perpendicular, whatever the central angle is, plus our inscribed angle, I'm going to call that, let's call them x and y. X plus y plus these two 90 degrees have to equal 360 degrees. We know 90 plus 90 is 180, so x plus y plus 180 equals 360. So whatever x plus y are have to equal 180, because I subtract 180, subtract 180. So this is why our circumscribed angle theorem says circumscribed angles are supplementary to the central angle. They add to 180 degrees because this shape that's created by the two radii, the two tangents, is a kite. And a kite has to add up to 360 degrees. And so if these two are 90, x plus y has to equal 180 degrees. All right, so we will come back on the next video and we'll talk about a couple examples of how to use this theorem.